I just wanted to start out with a recap of all the presentations that have been done here. And for people watching, either at home or on the recording, Cameron Castillo talking about our propulsion program, Andrew Robinson about mechanical, Hamir Sverson, I got that wrong, didn't I? The Golf Command and Control, Burns Fisher talked twice for the Golf Fox Plus telemetry and the whole orbit algorithm. And Kip Moravik was last there, up there with the EPS. And I don't know if you noticed, but there's a lot of talent we've got working for us, and that's only a part of it. But thank everybody who did come to present engineering stuff, if you will, because it's a great way, a great outlet for us. People are always looking for engineering updates, and pretty much I'd mumble something and they misquote me. So it's a whole lot better just coming from the people doing it. And like I said, there's many more. So we've got a lot of hard work that go into these projects. They're behind the scenes, I guess you'd say. But if you consider what it takes to do what they've shown you here, for example, in your lifetime, spare time, hobby time, you got family, kids, dogs, job, and all that kind of stuff, not to mention natural disasters and such. So it takes a while, but we built some really solid stuff. That's the thing. And in that, didn't mention it on that slide, but I mentioned just before the break that if you have more questions for any of these engineers who are talking up here, you'll have a chance to ask them, because I know there's probably a lot of questions, and some of them come to you, after you have a full belly or whatever. I'm just going to start with talking about the golf program, and then I'll pass it over to Mike to talk about Fox, and then come back to kind of end it with what we're doing in ASCENT. So Golf T and Golf 1, these are two satellites that hadn't been CSLI selected. They're part of what we call the golf program, because the intention is to have more than the two. Golf T is the technology, and I can't remember what I called it. Technology exploration environment, that's it. And Golf 1 then actually kind of goes back to our normal way of making satellites. And like I said, we'll get down to ASCENT with the SDRB. Too bad Ray couldn't be here, but you've probably seen it in the ads as SDR Gen 2, I believe. Microwave ground station, Jonathan, and propulsion, some guys, right? That was a neat demo they did. Some of them have asked, maybe all of them, that if you want to help with what they're talking about, please talk to us here. Even if you just want to inquire, and maybe nothing comes of it, but we need volunteers. And for the work that we need to be done, at least in these areas, there's no better chance for us to find out and for you to find out if you can help out. A lot of them are one-man jobs, or one-woman jobs, of course. And so that's another part of why it takes so long. We've got to devote ourselves to different aspects even within the project that you're working on. So we do need your help. Talk to people at home that are watching. Same thing for you. And you can reach out through, Frank, correct me if I'm wrong, email to help@amsat.org. Volunteer at amsat.org. Don't believe what it says on the slide. So email volunteer at and just mention the project or the person. Project and person would help a lot. And we'll get those emails and we can distribute them and actually hook you up to talk, so that as here, we can find out and you can find out if it's what you want to do. Golf T satellite. This is progress, changes, etc. Over the last year, basically. The purpose to develop and test our own design of deployable solar panels. Pardon me. Taking a lot of power. Kip talked about this a bit ago, to run a satellite that does any fun stuff, and that means a lot of solar panels, and they can be very expensive, especially for deployable things and things you can point at the sun. Now the ones we're doing are fixed, They will flop out, if you will, and you've seen. So we have to point them at the sun with the satellite, but it appears that they will give us the power we need to make it work. And that's what Golf T is all about. They want to test that to see if that design works and if that design provides the power we need at the level we're thinking. We can add more panels to that, so each panel could deploy 3, sorry for the P, they could deploy 3. Can you hear me if I'm here? Thank you. Say again? Thank you. I just don't want to pop P's there. Yeah, so we want to find out we can expand it, put a 3rd panel on each side, for example, if it's good, and that'll give us more power from a Golf 1, perhaps. For example, we've got a commercial, and it was always intended to be a commercial ADCS. Our first vendor, I think there's a little story about that later, but we're not flying the first one that we partnered with. They were a new startup, and so that gave them an opportunity to go to space and us an opportunity to get a cheap ADCS. We have our in-house designed RT-IHU, the radiation tolerant IHU, which was a ASCENT project idea, and during the Fox years, as the IHU, although it was designed to be able to reset and recover, did reset hundreds of times, right? And I don't know if that heat map is still good of where all the resets were, but most of them were in the South Atlantic anomaly until it got older in life, and then they started having more random places. So the timeout. All right, sorry. I'm trying to hurry because I think I started late there. The RT-IHU is flying against the LIHU, the legacy IHU on Golf T, because we know that the LTM, the legacy IHU, the improved command receiver, the transponder have flown before and are highly likely to work okay on Golf in case RT-IHU does not. So LIHU kind of watch over it, and if it works as good as we hope, it just won't have the resets that we do. Yeah, the RT-IHU, it's supposed to not have so many upsets. Flying against the LIHU, it also gives us an opportunity to test how a Fox 1, which we know how it behaved in a LEO as far as those upsets in the South Atlantic anomaly, and compare to that, and then the 10 gigahertz SDR is part of a high-speed telemetry and beacon test. It is high-speed telemetry at LEO on 10 gigahertz. It's not like we're expecting everybody to be able to capture anything, but the idea is to prove the concept that we can do it, among other things, and is intended for the higher orbits where we have higher gain antennas, slower passes, and such like that to be able to relay. Some years ago at CubeSat Developers Workshop, we had a lot of success with the Vanderbilt experiments on the Fox, and Burns mentioned the data under voice telemetry. And some of the universities were curious about flying experiments, and they asked me if we could do any higher data rates. They wanted like a megabit is probably slow on what they would want now, but so that's why this was put in here as an experiment. That was back in 2017. It wouldn't have done any good to scale it up right now because we're going to be pushing it just to test it. And all of these then must be flown as soon as possible. So it's kind of a tricky balance. It's so easy to get into pushing for perfection, to make everything work right because you want it to work, and that's how we build these things. But there are risks that we will have to take. And the idea is we want to know if the deployable panels work, if we can run an ADCS, THU, and the microwave works. That's all we need to do is prove that. It could, literally be up there for a day, but we don't want that. It does have built-in fallback. Because of the LTM, LIHU, it will do the dummy transponder, if you will. If all else dies, you can still use it, assuming battery or solar power. So, yeah, if these things all don't work too good, then the idea is we build ham radios in space, and we want one. So, there you go. the scheduled drivers for Golf Tee. I think I mentioned we had a launch at one time. In 2017, we found out the opportunity for these. It was approved by the board. I wrote the 2 CSLI. In 2018, February, I believe, we were accepted. And bless you, going through at a more or less typical pace. So in 2021, we were offered and manifested on a USSF launch. STP for their test program, S28B, Sierra 28B. It turned out that we were unable to do that because the vendor who was making that first ADCS did not deliver in time for us to keep up with the timeline for that launch. So we were able to back out of that. That's something you don't really want to do when you get a launch. NASA's going to pay for our launch, and you don't want to not show up. That's kind of not good faith, at least, right? Fortunately, it really kind of wasn't AMSAT's fault. They said, hang it on Ragnarok, try again. So that's followed immediately, practically, by the death of Bob Davis, our mechanical engineer at the time. I think I've mentioned that he had been with AMSAT since he got out of college, I believe, and doing mechanical engineering, and he knew a whole bunch about any of the satellites we'd built. So he was a great resource and also a very good mechanical engineer. With his loss, because we're pretty much, like I said, one man per project type of thing, we went and found some good new mechanical engineers, and that would be Tom Kranauskas, related to the guy back there in the corner running the show, and Dwayne, what was Dwayne's last name? Dwayne Moberg. Dwayne Moberg is working on the solar panels array, that part of it, and Tom is building the space frame, and which is quite a trick. You saw what was inside, and I'll show you some slides on that. But they were, and they're great mechanical engineers, but they're just totally new to the way, at least to the way we build satellites, which is, it's all homebrew. So, but we're making. Took a while to get them up to speed, but they're kicking butt now. So, and then of course the third thing that's a scheduled driver or HINC would be the complexity, because as Burns, I believe, said it, this is 3 times the volume of Fox 1. It's a 3U versus a 1U. It's 90 times as complicated. And I think I started that with 30 times as complicated just because it was a carryover of the 3, right? And we wound up upping that every so often. And what makes it goes in there that's so complicated, first of all, it's a first design. Fox 1, ultimately Fox 1A, was the first CubeSat AMSAT had built. And so that was the first design at trying to fit a bunch of stuff into a very tiny volume that, was preceded almost, if you skip over AeroSat a little bit there, but, AO40 was huge. And a lot of stuff to work with, a lot of place to put antennas. Fox is amazingly dense with capability, but that's what we're growing from. And to take that same idea that took about 7 years, I think maybe, to get to a launch, we were, in 2021, pushing 5 years maybe, which is pretty darn good. But it is still growing in the amount of the complexity that we encounter. So brand new design, you got to expect it's going to take a while, but it's going to be a very, very good design. Here's what I promised about the look inside. And this is a picture of, last year, of the model that we had. So I think the colors might have changed in the model that's here. I'm not certain, but they're still in the same position, basically. You got on the top there, your ADCS. This is going to be provided by or purchased from CubeSpace, which is a South African company. And they have made, and I believe flown, Burns, yeah? They've flown a few? Yeah, lots, okay. So they've made and flown lots. What we're able to get from them, the package is scalable as far as the size of momentum wheels and the sensors even, magnetorquers. And whether or not you need star trackers and such. So the pointing accuracy for Golf T is a couple degrees, I think, couple three maybe. And everybody seems to want better, so they were a little bit surprised by taking it at its bare bones. But we're just trying to point the patch antenna toward Earth or the panels toward sun, and a couple degrees won't make a difference to us on this mission anyway. You got your magnetometer for that sitting on the top there. The magnetometer does the magnetic field measurements, such as Burns was talking about in the telemetry. And I guess I had that blocked together before, but that's the Cube 80CS there. Cube Computer is the interface to our bus to talk back and forth between their ADCS and our IHU. And then our CIU. CIU is the Common Interface Unit, and it is a board, a matrix of different connections and cross-wiring and also controls to route all the wires that have to run, that don't run in the bus. You have to run wires externally to the solar panels, for example, and we have to have some wires to the, a bus to the ADCS. And so that handles all that. Also, it's involved in the separation switches, the safety RBF pin separation switches to keep the satellite unpowered while it's in the dispenser and getting ready for launch. The maximum power point tracking. That's a pretty good one. So this is what Kip addressed. I think it's got in little bits the MPPT here, and so this is not BMS. No, that was PDU. Sorry, that was a test. Thank you. You're awake. That's what matters. No, so the battery, yeah, the PDU, power distribution unit, and then the batteries down here. And there you go. How many we got in there?
8 batteries.
Thank you. I wanted to verify it, right? Because I think I wrote 6 on the NASA report or something. So yeah, we have 8 of the 18650 cells. And what are they, 3600 milliamp or something like that? What's their capacity? Don't remember. I think I remember that number from the wrong number I put on the NASA report. The 10 gigahertz SSPA. This is a bit of a trick, but the point of this in the picture is that it is heat sinked to the frame. We have some special metal around it, if you will, so that it can have contact with the frame there. And there we go. That's a sun sensor. We have coarse and fine sun sensors that could go everywhere, but when we were designing this, we didn't have that many everywhere to put it. So we do have it covered as far as what's required or necessary. And so there are other places, but it's not shown on here. The orbit grade GPS. In other words, this is one that will let you record high altitudes and fast speeds as in orbit. And that's connected with, it is not required by anything specifically, but it helps augment the ADCS to keep it updated on where it is, so it makes sure it's doing what it's supposed to. And it also provides use for us. It provides a clock, and that's all I can think of right now. So that is something that is mounted kind of weird to this. We call it the ADCS piggybackers. It's because if you look, it'll be on the next slide, but in this stack, which we call the transverse stack because it's not up and down like we like them, this is our standard avionics stack and bus. So it's got the LTM in it, Vanderbilt experiment card, and something else. Anyways, I'm going to turn it sideways here. Oh, and then there's room downstairs, if you will. Golf 1 is intended to carry a camera for a high school student experiment. It's been a long time since we, hook that up. So I don't know, they're probably graduated and waiting to do a job like this or something. But we plan to fly in some kind of camera experiment for students for STEM. And then also right now, it will be housing the Earth Horizon Sensor for the ADCS. It needs to look out at an angle so that it can make sure that it can discern the Earth from any other brighter source. And so it was kind of something else to try to wiggle in there because of the way it's designed and the angle it has to peek out the side. So one of those complex challenges. The 10 gigahertz patch array antenna by Kent Britton is on the bottom. I'm not sure I have a picture of it. It's a 4-patch antenna for 10 gigahertz. It's very broad beam width because in case we can't point it directly down, we can still use it. It actually works out that if it's, say, pointing down at you as it goes over, you can still work people off to the edge of the footprint because they can get into the sides. Kent says it's even got higher gain out there. So it gives the opportunity for the 10 gigahertz signal not to just kind of go swooping by, but be able to be heard throughout the pass more or less. The SSPA is, I mentioned it, enclosed for shielding there. Both RF EMI as well as then the heatsink. The EDIS E310. This is why we have a transverse stack, because we had the EDIS E310 radio. And we were expecting that we could modify it to be able to fit our 4x4 board footprint, if you will. And we found out early on that they wouldn't let us do that. So the only alternative, because at that time we were just into the CSLI. So we were pressing to move ahead to make that work. And so it is mounted, and you can see it's just longer than the other boards. And so that's the cause for the transverse stack. Now that will change when we get down to that SDRB, or the SDR Generation 2 is expected to be able to fit in there for hopefully Golf 1, and it's coming along pretty well. Vanderbilt ISDE experiment is stuck on the end of this. That's one of their radiation experiments where they look for upsets to various types of RAM and into even, what do they call it, like the 3D RAM that they use in GPUs and graphics and stuff like that, but I forgot what it's called because it's been years. But that's what they're going to be looking against. They look and see how many upsets they get, how when the pattern changes in the low Earth orbit. So that gives us also a little insight as to what the radiation is like over SAA, for example, where we're expecting to see RTIHU behave better. We got the fixed solar cell panels, and Kip went into this too about the MPPT, but the front and back, if you will, have fixed solar panels. I think the back one's down to only 6 instead of 7 cells because we needed more room to plug stuff in. And they got the RBF pin battery charge connection, umbilical connection, and some warning indicators there, and that's pretty much on or right next to the CIU. The active warning indicators are simply for ground use. If the satellite becomes active, you want to know it before it unleashes antennas or solar panels or something. And a little look at the solar panels as they deploy. You can see it again on the model there, but I thought a bigger picture on the screen might be helpful. So let's talk about that schedule. It is, you see the top purple circle up there? That's where we expect to have the full EM in a stack, basically, a satellite put together. Probably sans solar cells, of course, but to do the engineering model testing. And that's commencing just after the first of the year. Once we get along through that, about the end of March, hopefully everything's happy. Down at the bottom is the milestone for the CDR, the Critical Design Review, showing March 3rd, beginning of March in there, although that overlaps a little bit with the engineering model testing, so things have been sliding for quite some time. Then after that would be the flight model build and testing, with the expected delivery to come, well, call it a handover readiness date. we'd be able to deliver it and integrate it for a launch on, actually, we were shooting for September 30, 26. But I'm kind of thinking that we're probably gonna, because we have to look for a launch, we don't have the CSLI and such like that, that I'm gonna call it fourth quarter. So by the end, by December of 2026. And I have pretty good confidence about right now. CDR, of course, will either make me happier or knock me down. Now, so with the CSLI no longer available, we're looking at the need to, if we want to, and we decided we did, to purchase a launch. So it's about $300,000 for a 3U to LEO, and that's what NASA includes or as the cap on their grant. It's really a grant to pay for the launch. And so I think that the commercial price for that, you can probably, I'm certain you can shop around and find something less, but yeah, that's the value of what the CSLI provides us. And the current project schedule with the CDR in March does actually allow the time for us to wait until CDR, which I would anyway, before I purchase a launch, and see if CSLI is revived in whole or in part, because they're planning on having a review of the fact that they had to make the cuts in March. And so, being an optimist, you never know. I'm going to hang out and look for that. Yep, and there's that December 2026 date. So, Golf 1, there's not a lot to say about it right now. It's always intended to be about a year behind Golf T. We want to learn lessons from Golf T, and at the very minimum, it was learning as we construct it what works or doesn't work, what can we improve in the construction and design process, and it also gives us that opportunity to grow our skills and capabilities for making deployable solar panels, for example, and all the fun new complex stuff that's involved with it. It further establishes the microwave band usage. Now that's really important, pardon me, because the microwaves are where we have to go. First of all, we chose, and I recommended that we do the 5 and dime back when we had the CubeQuest challenge that we were providing communications package for. That would have been a lunar orbiter. And also the Phase 4B, which was going to be a GEO satellite that originally started out as being 3 and 5, I think, up 3, down 5. And I talked Bob McGuire into making it 5 and dime so that we have a kind of a compatible standard across several new satellites so that the users don't have to have a different kind of radio or more equipment in order to be able to talk to these things. By doing that, with the 10 gigahertz down, 5 gigahertz up, and then you've got 2.5 that will be on the satellite in order for the QL100 users to be able to use the thing without having to change their equipment. And the more that we populate that upper microwave stuff, first of all, it's too crowded below. It's just a fact. VHF, UHF, forget it. And especially when we get far away, which we will, you need to have smaller antennas, bigger gain, and the opportunity to fit that on a CubeSat. So it is the unavoidable future, I'd say. But we have, there's opportunities. We don't intend to leave anybody behind to move into the microwave RF field, I guess you could say. The ham radio microwave, the 10 gigahertz beacon, that's part of it. Because with Golf T, we have a little pickoff for the SDR to be able to see the 70 centimeter downlink of the LTM. And it's going to repeat that down on 10 gigahertz. So that passband, that downlink, will be available that you could work theoretically, VHF up and X-band down. That just gives an opportunity for people to get some 10 gigahertz equipment, try it out. And we're also working on a ground station in order to give you a leg up on what you can use, buy, or build. Also, the microwave, I understand, puts us in a grant, position us for a grant for opportunities for launches and such, for higher satellites, because of microwave, as well as all of them, while I'm here, will carry STEM experiments, educational stuff, if you will, because that's the future. So anything we carry that helps high schools, universities, middle schools, whatever. If the kids got a chance to build a board instead of a whole satellite and fly it and get some science, how can you lose? Well, I just said that, didn't I? And this was, since it had a CSLI, if CSLI resumes, we are back into the field of that. Now, Golf 1 was never going to go, well, it was intended to go to around 1,200 kilometers, because that's up there with AO29, AO7, and I thought, hey, since we're working our way back to HEO, the whole Gulf idea, if we had something up there, then, maybe if one of those fails or something, we can help, so to speak. And it also begins to stretch the capability for the microwave and such. Unfortunately, of course, the orbital debris rules changed, and especially the orbit lifetime down to 5 years. So that squelched that. What really killed it was the fact that there were no commercial means for us to get back down if we went there. There was nothing that had been used or approved for CubeSats. So despite the fact that there were ideas there, nothing had the 90% reliability, I believe, that NASA liked to say. And we couldn't fly 10 satellites to make sure 9 out of 10 of them worked, right? So nonetheless, all of this work we're doing continues to attract new and younger engineers. And you've seen that, I'm one of them now, but AMSAT was a bunch of old men for a little while, and it's just the way cycles go, right? Like your ham club or something. But we've got a lot of younger people getting interested in it, and it's great because it's the future for us. We can sit back and work satellites all the time, and they have new ideas, better ways to do things, different ways to do things, and the keen thing about that is that that's what other kids, younger people, are going to get into. And if you're a diehard old guy, you're going to figure it out too, because you like to do that stuff, right? So it's a great position to have younger kids designing, building, and taking over. I think that's all I have here for golf. Fox Plus up next, but at this point, if you have any questions for me, or as I mentioned earlier, if you have any questions for any of the engineers who were speaking previously, especially about anything that was golf related, if you could make a distinction, but let's do that. It'll take a little time right here. What time is it?
My question is about the lithium cells. I know it says lithium ion and the 18650s. I'm talking about rather than lithium iron phosphate. What is the reason for that?
See, I cannot answer that. I don't know that. Our battery guy, if you will, he's not here, so we could find that out. Any of our other engineers remember what was said about that, or if anything? 18650s have been on our mind ever since back in 2017, I guess. And the way that Doug is working with all this stuff, he works in the automotive battery industry, if you will. So we would want it that way, and of course range safety and everybody wants it that way. But we don't see any problems with the way that they're used. But if you think there's something we don't know, I'd sure like to hear it, because that's where, that's how you correct things, right? Other people looking.
Yeah, I've been dealing with lithium cells for, I just finished kind of a 14-year, let's call it experience, because I was retired and not a study, using lithium iron phosphate in an electric car that I built. And so I installed 48 lithium cells in 2011, and after 5,000 cycles, the cells were down to 75%. I replaced them at that point. And So they're lithium iron phosphate. And another reason they're chosen is because they don't catch fire, and it's a good safety concern. Basically, the iron grabbing up all the oxygen molecules, and so it doesn't really support flame. And I don't know how that works in space, but the thing was that another reason for the choice was the number of charge cycles. And in that presentation, it said, well, we got this enormous number of charge cycles, and trying to predict the number of charge cycles. And during this 14 years, I've talked to a lot of researchers who were working on behalf of the automotive industry, trying to come up with how do you predict the lifetime of lithium cells. And there's no equation. Engineers, give us an equation and we figure this out. Product lifetime. And so then when I saw lithium ion, I thought, well, they don't get as many charge cycles. So what was the priority here? And I'm sure, it was carefully chosen, but that's why a question popped up in my mind from my own experience.
I'm going to, the cell number and such on here is not as new as what I misstated in the NASA report I was talking about. That's where I did find out the specific cells from Orbitron and model number and such like that. So there may be something in there. I've got it on my PC, that report is sent. So I'll take a look at that and see if it says anything different. And the lithium iron, you got LiPo, right? And then what's the lithium iron? And
lithium iron phosphate.
Yeah, but is there the abbreviation? I mean, do you call them
LiFePO4?
LiFePO?
LiFePO4, yeah.
Yeah, okay. And I've heard that. I just wanted to make sure. Mm-hmm. So, yeah, I can check that. I can at least check out exactly what it is because I just ordered them. So that was cool. Yep.
Really quick, I've flown 40 satellites with NICADs.
Yeah.
You can't hurt them. They will charge and discharge forever. Why not NICADs?
We flew NICADs on Fox because at a minimum that I know of, because I joined, after that program actually started, but there was no information, no data on lithium, how much they could take as far as cycles and such like that. We flew A cells. It was designed for A cells to hold 6 A cells. And we sourced them through what was then, I think, Batteries America. Everett, don't recall his last name, but he actually went and found some and matched sets. He made us 5 matched sets, which was really cool. That's part of why we got 5 satellites out of it. And he said at that time that after that he would not be able to source any more reliable, non-junk consumer NICADs, at least in that size. So that's part of the reason we drifted away. We went away from that because of that, but also the expertise that we have with us as far as doing the lithium, which honestly, it was kind of funny because on the Fox 1 launch, I confused the range safety that, by saying that we have these NICAD cells, and they made me short one out and blow it up to prove that it wouldn't blow up, which it didn't, but it sure gave us a jump. So it's like they didn't even know what a NICAD was or something, But we went to lithium because it's just, we could not find any suitable NICADs anymore that weren't junk.
Don't forget that all of our satellites with NICADs fail because of batteries.
Well, that's true, but it fails because we mistreated them. Yeah. We ran those things full bore all, their whole life basically. So, and you could say that's my fault because I knew Tony Montero, my predecessor, had preached 20% discharge cycle, and I'm dumb, I guess. So I didn't realize that we were exceeding that until they all died, and then I went, maybe that was it.
We're golf one. Well,
Hey, dude, yeah, I got you.
For Golf 1, are you considering a 1,200 kilometer circular orbit, or is it a more elliptical orbit?
I'm dreaming about a 1,200 kilometer. We won't get that
You won't
because
get
we
that.
can't come back. Yeah, that launch opportunity offer came and went, probably 2019, I think. Yeah, it might have been 20 or so. It was just before COVID. I know that. I remember that much. So we're not seeking that now, and with the current CSLI, our mission manager, thank you, mission manager, NASA, one of which was Liam, had suggested you're not going to get above like 550 or so anymore. So I settled for that. It's like, well, that's it. Because even then, that stuff was starting to come to market just in the last couple of years for CubeSats. And so, but that was too late to take an opportunity for that. I'm not to say it might not come along if they reawaken it, with CSLI. That would be great. We'll go if we can stick something on it that's suitable. Heck yes, I'd go. That's like, but we can't. So the whole point is we're going to use it to still learn ADCS and the control of the satellite pointing, power, and also we have that propulsion team that hopefully you saw their stuff yesterday. And in LEO, some opportunities to test that out, because I know if we flew a satellite to HEO right now, we'd be using commercial propulsion and probably commercial a lot of stuff, because we just don't know how to make that work. You don't want to run into everybody, and I call it Starlink pinball. But so playing with that, if you will, in LEO with the 3U, and we'll consider how to get to HEO next based on whatever opportunities are, or even 1,200.